sparked by an unfortunate accident where a New South Wales senator's wife was hit by a mobility scooter. There's been a long-running debate in Australia about severely regulating the use of mobility scooters and other small-scale electrical vehicles. But these devices, broadly known as personal mobility devices, have not only helped those with disabilities, but are soon becoming an important part of a smarter, cleaner transportation infrastructure. So my thesis focuses on adapting the massive advances we've seen in the self-driving car industry in an attempt to improve the safety and functionality of these devices so that we can still reap their benefits but minimize their harms. Now, the first challenge in doing so is solving what is known as the pose estimation problem. Now, contrary to science fiction, unlike you or I, a robot starts out as an inanimate object with no sense of where they are in space. So a robot has to figure out its pose, basically its position and orientation in space based off its sensors. And this is a fundamental problem in robotics research because if you don't know where you are accurately, you can't make safe navigation decisions. Now outdoors, you would expect something like GPS to solve this problem. But anyone who's used Google Maps would know that it's just not accurate enough, especially in an urban environment with buildings blocking out the skyline. So most in the autonomous driving industry rely on a suite of sensors, with these really expensive laser-based sensors called LiDARs being the favorite. Now these make sense in a fast-moving car, but for a low-speed, resource-constrained application such as ours, cameras or broadly vision sensors offer a far cheaper alternative. There are broadly three approaches to the pose estimation problem. The first is dead reckoning, which involves using sensors like wheel encoders and IMUs. The best analogy of this approach is imagine you're blindfolded and told to navigate by only counting your footsteps. As you would imagine, this isn't the best approach, but it does form an important part of the larger solution. The second is localization. Now, this involves using a pre-built map of the environment. So you're still counting your steps, but you've also removed your blindfold and you have a map with you. So you can look around at things like landmarks and features and match it to the map and get a better estimate of where you are. So localization is great if you have a pre-built map. But what do you do if you're in a completely unknown environment or you want to build that map in the first place? Then you have to rely on this third technique known as simultaneous localization and mapping, or SLAM, where you're simultaneously figuring out where you are while also building a map. This is kind of like a chicken and egg problem because to localize you need a map and to build a map you need to know where you are. So it's a much more complicated problem and it's computationally expensive, and all the tiny errors that get made along the way add up and you can start to drift away from the true location. This is a big problem in large-scale outdoor environments, and the only way to fix it is by revisiting places you've already been to and doing what is known as loop closure. But that's not a very efficient way to get from point A to point B. So it's clear, if you're in a known environment, localization on a pre-built map is the most efficient way to navigate. And this is fairly straightforward if you're using one of those expensive LiDAR sensors, because extracting geometric features from a LiDAR-based 3D map is a comparatively simpler task. But here's the catch, if you're going for the more cheaper, compact alternative of cameras, you're forced to use SLAM or odometry. This is because the types of features most state-of-the-art vision systems extract look like this. Now, it's really hard to make a pre-built map of these kind of features because they constantly change with lighting, with weather, and even moving objects like cars and people. So most vision-based systems have to rely on SLAM because it doesn't require a pre-built map. But as I mentioned before, if you're in a known environment and you just want to get from point A to point B, SLAM is computationally expensive and unnecessarily complex. So this is where my thesis comes in. Instead of using those traditional feature detection methods, we use a deep learning technique known as convolutional neural networks, which help us detect more higher level persistent features in the environment so that we can do vision-based localization on a pre-built map without having to rely on SLAM or LiDARs. We do this in two ways. We first use a CNN called YOLO, to train it to detect things like lampposts and trees, basically landmarks in a pedestrian environment. We then build a simple 2D map of the locations of these features. Then we use another CNN called HED to extract important ground surface boundaries related to features such as curbs and pavement edges and manhole covers. We then build a map of these features using a representation called a vector distance transform, which essentially encodes how far away you are from these boundaries. We then statistically fuse all this information with odometry data using this technique known as an extended Kalman filter, or EKF. The EKF is a standard statistical algorithm that helps you estimate uncertain quantities based on the information you have at a given moment. The word uncertainty here is important because no measurement or sensor can ever be 100% accurate. So it's not just important to know where you are, it's also important to know how certain you are of your answer so you can make smarter decisions. This approach was tested on the following modified mobility scooter platform. Using this hardware platform, we conducted experiments in an almost 8,000 square meter area in Glebe, Sydney, which is representative of a typical urban environment. Results show we outperform traditional state-of-the-art systems in terms of accuracy. We have also explored the idea of replacing the multiple cameras with a single consumer-level 360-degree dual fisheye camera to improve the field of view of the landmark detection system. Here we developed an algorithm that predicts which direction to look at so that only that viewpoint is processed at a given moment instead of the whole 360 image, improving processing requirements and fixing fisheye distortion. The final contribution involves constraining the pose estimate to drivable areas in a map, since in most cases these devices drive along predefined paths bounded by fences, walls, or the curb, and then statistically determining cases where you could intentionally drive out of the path if the path is bounded by, say, gravel or grass. Incorporating this information has significantly improved the overall accuracy. The primary contributions of my thesis that I just outlined all focus on the pose estimation problem. So in terms of future work, the next step involves looking at autonomous control strategies. In the case of the mobility scooter, we believe that a fully autonomous system could be detrimental to the feeling of independence and self-reliance experienced by its end users. Thus, our future plan is to explore shared control strategies between the driver and the robot, where the robot will be fully capable of autonomous driving, but will mainly act as a guardian system that only steps in to prevent potential accidents. This is a full list of publications and other awards this project has achieved, including coming third place at the Dubai World Challenge for Self-Driving Transport in the academia category, which was a fun experience. None of this could have been possible without the support of the following individuals who have helped this project at many capacities. So, to end this presentation, I will leave you with a video that I submitted for the Visualize Your Thesis competition, which I hope will serve as a summary of my presentation. Thank you. Meet Betsy. She's sweet, she's wise, she's old, but she's also an absolute rebel. For Betsy and many like her, a mobility scooter can be the only way to hit the open road or just get the groceries. But these scooters have raised some safety concerns, especially because they're invading spaces reserved for pedestrians. What if we can improve their safety through innovation? What if we take self-driving car tech and chuck it onto a scooter? But wait! Most self-driving cars use expensive laser sensors and heavy computing to navigate. Bye-bye Betsy's pension. But aha! By combining deep learning and a modified navigation algorithm that was used in the Apollo moon missions, we've created a system that can accurately navigate with just a few cheap cameras and modest computing. The whole package coming at almost 1/4 the cost of a single LiDAR. Well, hello, Betsy's pension. So, Betsy, give it a try. We haven't squeezed all the fun out of it. Our system only acts as a co-pilot and will only step in if horrible accidents are about to happen. So you still get to be that independent, badass, sweet old lady that you are.